This video is going to cover section 5.9, volume of a solid of revolution, and today's day 1, and we are learning the disk method. What I'd like you to do first is partner up, and with a partner I want you to calculate the area under the curve of f of x equals the square root of 9 minus x squared. Now I want one of you to calculate the area using definite integrals, and the other one I want you to calculate the area using a method that you previously learned in another math class. So go ahead and pause the video and then come back to check your answer. So I told one of you to use a definite integral to calculate the area of the semicircle under the curve, and your definite integral should have looked like this, negative 3 to 3 of the square root of 9 minus x squared dx, and you got 14.137. The other one of you calculated this area most likely using the formula pi r squared, which is the area of a circle, and then just dividing it by 2 since it's a semicircle, and your answer should have matched up. Now the same thing, what I want you guys to do is using that area, I want you to figure out what shape would be created if I took that semicircle and I revolved it around this x-axis and it made a three-dimensional object. I want you to think about what shape is created, and I want you to calculate its volume. So go ahead and pause the video and determine what the volume of your shape would be. So some of you probably said that it would create a sphere, and you are right. And so the sphere formula is 4/3 pi r cubed, and the radius in this case is 3. And so you should have gotten a volume of about 113.097. Now what we're going to learn today is what if I want to revolve this shape or this area around the x-axis, and it's not just going to be as simple as a semicircle, so it's not going to make a sphere. What if it is a quadratic equation? It doesn't make a nice sphere. What if it doesn't make a cube? What if it doesn't make a nice cylinder? How do you come up with a formula to calculate that volume? And so take a look at this picture. So it's still our semicircle example. I've drawn a rectangular strip in here because area has always been the sum of all the infinite number of rectangles going from your limits of integration. Think about revolving this rectangle around the x-axis. What three-dimensional object is created? And so I have an animation to help illustrate that. So here's our square root of 9 minus x squared, and here's our rectangle. I'm going to revolve it around the x-axis, and I want you to see what it creates. And that one little rectangle creates what we call a disk. So it's kind of like a compact disk, but without the hole in the middle. Or another way of looking at it is like a squished cylinder. And so to find the volume of that, since we're going to find the volume of this entire object being revolved around the x-axis, let me show you some other disks being revolved. Now this is a finite number. I think this is only like 8 or 9 disks, but remember, the more rectangles you use, the more disks you use, the more accurate your answer is. And so we won't have to worry about it being kind of chunked at the end. It would be a nice smooth sphere. And so area under the curve is the sum of the area of all the rectangles. Well, volume is just going to be the sum of all of these different disks being added up together. And so think about the volume of a disk, kind of like a cylinder. So we start with pi r squared as our base, and then we multiply it by its height. And in this case, if I go back to my very first rectangle, the width of my disk is going to be this dx. And so going back, the width is dx. That doesn't matter what that is. It's not going to be a numerical value, but the radius is going to be the distance, or the vertical length of my rectangle, and that's just the formula, the function that you're given. So using a different example, here is f of x equals x to the 1/3 power. We're only going to focus on the first quadrant, and we're only going to go from 0 to 8. So if I were to draw a bunch of different rectangles in, the heights are going to be different, meaning my radiuses are all going to be different heights. And so we want to use what we call a generic radius, and in this case that radius is the height of each rectangle, which is our function. So x to the 1/3 is our radius. And so to calculate the volume of this object, and if you kind of think about from 0 to 8, it's somewhat of a parabola, but if we were to revolve it, it kind of looks like a lampshade on its side, a curved one with no middle being chunked out. It's full, it doesn't have any gaps in it. And so the generic formula for volume using disk method is volume equals pi of your definite integral a to b of r of x squared dx, and this is vertical slicing, so your rectangles are vertical. And so if you kind of look at this, here's the pi, that's my constant, pi r squared, that's the area of my circle, my base, and then the width, my dx, would be the height of my disk. And so then it's just from a to b, whatever your limits of integration are. So back to our example, f of x equals x to the 1/3 power. My pi goes out front right away. My limits of integration, I said I only wanted to do the area from 0 to 8. Sometimes those will be given. If you're given multiple equations, sometimes it's their point of intersection, so you'll have to calculate that. But in this case, I told you I wanted to go the area from 0 to 8. Of my radius, my function is x to the 1/3 and then squared, so pi r squared. In the simplified version, it's pi of the definite integral 0 to 8, or sorry, pi times the definite integral 0 to 8, x to the 2/3. And then you can use Math 9. Some of these you might have to do by hand. But the one thing you don't want to forget to do is to multiply by that pi. So when you do the definite integral, you get 19.2 times pi, and it should be approximately 60.319. One more example, calculating calculating volume using the disk method would be the region that is in quadrant 1 bounded by the graph of f of x equals negative x squared plus 4 and the x-axis about the x-axis. So this is my an upside down parabola, and I'm only focusing on the region in quadrant 1. And so I kind of tried to color it in for you in red, and we're going to revolve it around the x-axis. And so the setup for this would be volume equals pi, and then since we're only focusing on the first quadrant, 0 to 2 are my limits of integration. These are x values. And then my radius is just my function, because the height of each rectangle is just the y value of that rectangle. And since we're using an infinite amount, we're just going to use f of x, and then don't forget to square it. Type that into Math 9, and you should get about 53.617. This, of course, is including the multiplying by pi. Disk method isn't always just going to ask you to revolve your region about the x-axis. It might ask you to revolve it around y equals 1 or y equals negative 4. And so here's an example. I have f of x equals 2 minus x squared and g of x equals 1. The region bounded by these two graphs, so if you think about calculating the area between those two graphs, the next step is just to put it into the volume formula. So the picture looks like this. Here's my function, 2 minus x squared, and then my line y equals 1 or g of x equals 1. And so this region that my cursor is tracing is the region that we're going to revolve, but we're not revolving it around the x-axis. That we will learn how to do tomorrow. Today we are learning how to revolve it around y equals 1. And so this area around the line y equals 1, what I need to worry about now is what is my radius going to be of each of my disks. And so just my next slide. You'll notice that if I were to just revolve around the parabola or the quadratic area, my radius would be the equation of the parabola, 2 minus x squared. If I were just to revolve the area g of x equals 1 around the x-axis, that would be my other radius. But now I wanted to just show you that visual that my rectangular slice is going to be up in this area above my small radius. And so this is very similar to calculating the area between two curves. I need to know what function is greater and what function is the lesser curve. So the generic formula, when you have to revolve your area around another line, you might have to subtract two functions. And so in this case, here's my pi. My radius now is the difference between my greater function and my lesser function. It's still squared, and then I'm going from a to b, which in this case would be my points of intersection. So I would set these equal to one another and solve. And so you get negative 1 to 1. And then plugging that into Math 9, don't forget to multiply it by pi. You get 3.351. And the very last part of calculating volume by revolving is what if you're going to revolve around a vertical axis of revolution or use a horizontal rectangular slice. So here's an example. Calculate the volume of the solid of the region in quadrant 1 bounded by the parabola y equals negative x squared plus 4 that is rotated about the x-axis. And so here I'm using, I did say quadrant 1, so I just didn't color this in red this time, but since I'm revolving it around the y-axis, I have to change my rectangle slice to a horizontal because with volume by revolution using disk method, we always want our slice to be perpendicular to the axis of revolution. So if I tell you y-axis, you know instantly that you're going to use a horizontal slice. So what we have to do here is similar to what we had to do with area of horizontal slices. We need to change our equation from a y equals to an x equals. So I'm going to go ahead and subtract 4 from both sides, then divide by a -1, and then the last thing I'm going to do is take the square root. Now usually when you take the square root there should be a plus and minus out front, but the reason I'm just leaving it as is because it's just the positive, because I'm in quadrant 1, so I only have to focus on the positive x values. And so then my radius is going to be that horizontal distance, and then the one difference with your horizontal slices is that you are your limits of integration are no longer x values, they're y values. And so we're going to be going from 0 to 4. And so my example here is still going to be pi r squared. So volume equals pi, but now I'm not going from 0 to 2. I'm going to go from 0 to 4. And then my radius is now the square root of -y plus 4, and then square it, which that does simplify to just the integral of -y plus 4. The square and the square root cancel out. You can still just use Math 9 for this. Your calculator does not know the difference between x's and y's. It doesn't know that you're using a horizontal slice, so it treats this the same way it would as if this had been an x. You'd get the same answer. Just don't forget to multiply it by pi, which in this case you get an exact answer to be 8 times pi, and you get 25.132. One thing I want you to know is that when you're calculating area between curves and volume, your answers should be positive. Yes, you can get area under a curve to be negative, and that's when you change directions or it's when it's under the x-axis, but area between two curves and the volume should always be positive. So kind of just a little recap of using disk method by revolving regions around an axis. Vertical slicing, remember it should be a y equals equation. Horizontal slicing, it should be an x equals equation, and your limits of integration are y values. And then if you're rotating about a line that's not the x or y axis, you should be subtracting two functions from one another to get your new radius. And this also does apply to horizontal slicing. I just didn't go through an example of it. So now you have some time to work on volume worksheet number 1, and the answer key will be on Moodle. Have a good day.